So good morning, everyone. Welcome to the National Training Workshop on Paleoclimate Archives, Proxies, and Analysis and Measurement Techniques. My name is Dr. Shikha Singh, and I'm one of the organizing members of this workshop. This is one of the first workshops of this year at IITM Pune, and I welcome you all here. And I'm sure you all are very excited for it. So let's begin the inaugural session. To start off, I request the dignitaries to please come on stage. I request Director IITM, Dr. R. Krishnan, to please come on stage. I request Dr. Shushma Prasad to please come on stage. I request Dr. Vinita Patia to please take a seat on stage. And I request Dr. Naveen Gandhi, convener of this workshop, to please take a seat. I request Dr. Gandhi to please welcome Dr. Krishnan to the plant.
Thank you.
I request Dr. Gandhi to please welcome Dr. Shushma Prasad. I request Dr. Gandhi to please welcome Dr. Vinita. I request Vaishali to please welcome Dr. Gandhi. So, I request Dr. Krishnan to please deliver the welcome address.
Thank you, Shikha. Good morning, friends. Dr. Sushma, Dr. Vinita, Dr. Naveen, all my old friends here. I'm very happy to see Professor Ravi Bhushan, Dr. Bolgaonkar, Shreyas Managabe, Dr. Rajni, Gyan Rajan Tripathi, so many people. Dr. Karthik was also in the MOS project, and so many young participants. So I wholeheartedly welcome all of you to this workshop on National Training Workshop on Paleoclimate Archives, Proxies, Analysis. Very lengthy workshop. Yeah, lengthy paleo. And I should thank Naveen. He's taken a lot of initiative. He's planned it very meticulously to organize this workshop. Along with this, we do it in full support from CCCR, Dr. Milian, Dr. Sanjay, who have supported. And I think they have very systematically planned this agenda for this workshop. So I really appreciate their efforts, and I welcome you all. It's a very nice time in February, January. Sorry, it's a very nice weather here. So please enjoy your stay. And yeah, if there are any problems, please let us know. And it's a very fascinating subject. Looking back at how climate has varied in the past, and of course now human activities have been altering. So what will happen in the future? That's a very interesting way of looking at the subject. But there are also a lot of uncertainties when you're talking about regional scale processes. I mean, those things I will tell during my talk. I don't want to get into those details. And it's good to see so many experts. At IITM, it started with Professor J.B. Pant, our former director. He started the training dendroclimatology group at that time. Then later on, Dr. Bolgaonkar was looking after Dr. Kumar and Bolgaonkar. Then Somaru was there. Now, then Naveen later on subsequently joined. Supriyo Chakravarti was there. But he moved into more of medflux. So that was his, he was mandated with that task. So So, but now again, I'm very happy that Naveen has taken up this looking at the speleotherms and other cave deposits and so on. So I think you need multiple proxies to really understand this, how climate has really varied in the past and try to interpret that. And so I think this topic is very, very relevant. And it's very nice to see so many young people. And so I welcome you all, wholeheartedly welcome you. Please enjoy your stay and please feel free. If there are any problems, please let us know. Yeah. Thank you very much.
Thank you, sir. I now request Dr. Naveen Gandhi, the convener for this training workshop, to please speak on scope and objectives of the workshop.
Thank you, Shika. So good morning, everyone, and welcome to the IITM. So as Dr. Krishnan says, and Shika also, it is a kind of new initiative, and this is after COVID outbreak, we planned first time of in-person workshop. So it all started with one Saturday meeting with UK working, if you remember, before Diwali. So just during discussion, this idea came, and then very next day, I contacted our local ISER and other research friends and Pune University. So everybody chipped in, and then next day, Monday morning, I went to Dr. Vinu, and he immediately accepted. He actually liked that idea, and then he forwarded everything to Dr. Krishnan, and he also approved this workshop. So this is how all started, and because this is something kind of new initiative here. So initially we thought of just selecting 25 students. So we thought we can handle this much, but later we got so many applications and the overwhelming response. We almost received 300 applications. So then selecting out of 325 would be very, very difficult for us. So we actually increased almost to double. 50 students we selected actually for this workshop. And then just as name suggests, in this workshop we are intended to provide some basics. What is the importance? Like what are the challenges? What are the unanswered questions? So Dr. Krishna will talk about something. So why actually we need to do this? Then Dr. Sushma will tell you more what is basically the paleoclimate is and how we can pursue it. Then we will be learning many things about what are the archives where the climatic signals are actually there, and what are the techniques, what are the proxies from which we can actually extract those signals and to understand the climate changes. So this is and we also have some basic techniques which are we are using for this, for carbon 14, because the revolution is here. Then OSL for dating is also there, is required. So those training will also be part of this workshop. And when we get the data, we have to do some statistical analysis because these paleoclimate data is unevenly spaced data sets. So, but like you might have studied about the Fourier transform and getting the spectrum analysis, but there the data sets are always equally distanced. But here we get the unevenly spaced data. So how to deal with those data sets and get the age model, then get the periodicities, then do the wavelet analysis and do the coherence analysis. So those things also will be learning in the workshop. So in first half every day morning to lunchtime we will be having lectures, and in second half after lunch we'll be having lab trainings in hands-on trainings. First day in IITM, and then subsequently in ISER, Pune University and other research institute. And the last day we would be going for a field work that is around 100 kilometers from Pune. There are 2 geological sites. So the experts are here, they will more elaborate. I am not expert on these things. So I welcome you all, and I hope you will learn, and most importantly, you have to be punctual in all the lectures and even the field work. Okay, so thank you all coming from all the way to different parts of India. Thank you.
Thank you, Dr. Gandhi. So This workshop has been organized as a part of activities of the Association of Quaternary Researchers, AOQR. Dr. Vinita Partyal amongst us is a scientist at Iber Sahani Institute of Paleosciences, Lucknow, and is one of the founding members of AOQR. She is also the present secretary of AOQR. I request her to please brief about the activities of AOQR.
Good morning, everybody. Dignitaries on the dais, Dr. Krishnan, Dr. Sushma Prasad, Naveen, the organizer of this conference, and dignitaries of the dais, my colleagues, my mentors, and dear students. So, as Dr. Krishnan said, that paleoclimate is a very complex thing. So, this workshop is designed to for you to understand the complexities of paleoclimate. Like, it's not just one proxy, you have to deal with it with multi-proxy. And you have to understand that all the proxies like physical, chemical, and biotic proxies are important. To start with, as Naveen said, this was just October around Diwali last year that we had an online meeting, and this module was developed. And with lightning speed, like Naveen took things on hand, and thank you all the mentors here who were ready to conduct this. And thank you for your support, Dr. Krishnan, to make it happen in IITM. AOQR, as Naveen said, that it is an association of quaternary researchers in India. We are just 3 years old. I invite you all to become members of AOQR because it is the mandate of AOQR to conduct such trainings, workshops, and conferences. Last year, we also started this Indian Quaternary Congress. We had associations of different groups, but for Quaternary, which is the largest group, in India, because every institute, educational institute, be it the IITs or the ISERs or the state universities or central universities and many more institutes in India, because India is blessed with so many, academic institutes. Everywhere, quaternary researchers are going on. So we wanted to bring everybody under one platform, and we felt this because in 2019 in Dublin, when we were there for the INQA, which is International Quaternary Association, it's a congress, it's a global congress held every 4 years. So when we were there, we were bidding for 2023. This year we wanted it to be happen in India, but we lost the bid. We found out the reason why we lost the bid, although there were like 60 people participants from India in Dublin, reading the papers and presenting the work, but we didn't have a close, association with each other. So after coming back in 6 months, we just got on it and we got this association registered under the Societies Act. And since then, we have members there. We have a website. Please go through it. You can see it. And there you will get first-hand information on what we are doing and what is AOQR planning in the future also. So just become members of that. It will be really nice. This meeting was funded by DESC, so thankful to them. Otherwise, the meetings for the AOQR members, those are free. Otherwise, we charge a little amount from the students, and that's really not good also. But because we are growing and we need funds, so that is why. So that is why I'm saying to all of you to become members of that association. And we'll have lots. The mentors from all over India, they have taken out time for you students to, come here from their busy schedule and deliver their talks to talk to you about the paleoclimatic proxies. This was the physical and chemical proxies this time. Next time we will do it for the biotic proxies. It can be any place in India as venue. So please be attentive, as Naveen said, listen to all the talks, make notes, be on time, and take home the knowledge that is being imparted here. It's a seat of learning. So just be very attentive, and you all have to develop on those ideas, implement on those ideas for your career if you want to come do paleoclimatic research in the future, which is very important, which is needed in the country. So with these words, we talk more when the session is there. And I thank you again for inviting me, having me here. I thank the IITM director for all the facilities here and making this happen here. Thank you.
For such encouraging words. I now request Dr. Sushma Prasad. She is a professor at University of Potsdam, Germany. I request you to please say a few words on this inaugural.
I think I need a step stool to be visible from here.
Good.
And I have been trying to hide, so I didn't prepare any remarks. All I can say is, paleoclimatologists and modelers, we always tell the other, you don't know what you're talking about. I think most of it is because we don't understand each other's language. Modelers speak in different terms, terminology, time scales, whereas for us it's different, the archives we're dealing with. And I'm glad that IITM and Naveen have taken the initiative to bring both the teams together to encourage this type of communication. And hopefully the younger generation will benefit from that. Thank you.
Thank you, ma'am. I now request Director IITM to present the keynote talk and challenges of the
I don't have a formal talk as such. Naveen asked me to give some presentation, but I'm not the best person. As Sushma was telling in the beginning, this is where both the observation people who are working along proxies and archives, and the modeling community, they have come together. So it's a very fascinating topic. So having said that, when we look at global signals like the glacial periods and interglacial periods, or where the global temperature has increased and it has dropped, we roughly understand them because the main constraint is the solar energy. So if there is a change in the incoming and the outgoing radiation, and you have a atmospheric layer surrounding the Earth, which is having all these greenhouse gases and like water vapor and carbon dioxide, methane. So they are going to alter. So the atmospheric chemical composition becomes very important. And also the albedo of the planet, how much is coming and what fraction is reflected into the space. So these are so as a first order balance, it's basically a radiative energy problem. How much energy is coming and how much energy is going out. So, and we have the different absorbers, and that determines the mean state of the mean climate, global mean climate. And so changes in the composition for whatever reason, it may be due to geological activity, due to man-made activity, changes are due to volcanic eruptions, or irradiance changes, may not be composition, due to orbital parameters, sun-earth orbital parameters. So you can have climatic variations on different time scales. But when we come to regional scales, especially when you are talking about monsoon, which is a very important regional phenomenon, how to utter it, so that becomes a challenging issue. And so now there are there could be, some people have talked about all this upwelling foraminifera in the Arabian Sea. Some people say that, okay, we will look at precipitation, oxygen isotope from cave deposit. And Ravi Bhushan, I know he works on corals and does many other things. He's also working on coral records, sea surface temperature variations, and so on. So there are multiple proxies. Again, it is adding more complexity. So there is a problem, we are adding more complexity, and there are different time scales. So one is so basically climate is a forced problem. You have could be forced by some external forcing, and then there are interactive feedbacks within the system. The time scales are very different because you have the land, the atmosphere. So the heat capacities are very different, the response time scales are different. So the interactions can be very, very different. And so you have all these variabilities during each climatic epoch, I would say. You could have El Ninos, you could have El Nino Southern Oscillation, decadal type scale oscillation. And now people are telling same thing can happen in the Atlantic as well, or in the Indian Ocean. So it's really very complicated signal. So when you are looking at why precipitation variations are happening during this time, so it is important to come out with a good assessment what really happened to the Indian monsoon, the South and Southeast Asian monsoon. That, according to me, is an important problem. In the last, let us say, 20,000 years, can we come out with step by step what has happened? And I don't know if such assessment, systematic assessment is available. So IPCC, we did make what are the observed changes in the latest IPCC report, what are the past changes. So we have to find out what further we can go ahead. And it is not spatially uniform. Somebody there is, Naveen has some proxy from the Kadapa caves, Sushma has a lake sediment proxy from Lonar, and there are some proxies coming from North India. So are we all telling a common story? That is going to be very important. Each person tells one thing, this, and then we are adding more to the confusion. Already there is confusion, we are adding more confusion to that. I think that is important to resolve. And modeling, people look at constraint. What is the constraint? What really happened? So they say, okay, 6,000 years back, mid-Holocene, maximum solar insolation was there, the orbital parameters. So we know how to prescribe that. There were vegetation changes, green Sahara was there, dust was reduced. So prescribing the constraint is very important. So these two, according to me, are very important. So take-home message, can we come with a good assessment for the monsoon in the last 20,000 years, how it has varied, and what are the constraints that these proxies can provide for the modeling community. So these two, and any other interesting topic. Now people are, so now they start telling that this mode of variability is there, that mode. If we do a spectral analysis, we are going to get all kinds of modes. And so that can also lead to confusion. Because there is a paper by Michael Mann. He has recently, he says that all these modes are, they are all expressions of volcanic eruptions or anthropogenic forces. In science are conscious. So many modes, I think, especially on the multi-decadal and things, kind of says that it's not how true it is, we don't know. So that is came in 2020 or so. And now people are telling there's a 4.2K event that took place. Many areas experienced drought, and some people have actually challenged the 4.2K. So there's an opposite view. So I think as paleoclimate people, we have to take what is our stand on the monsoon. And did the Indian monsoon really collapse during 4.2? Was it related to the 4.2 event? So these are some big questions that we need to ask. So these are my thoughts. So with this, I stop and wish you all the best. Please enjoy your workshop.
Thank you, sir.
Yes.
Now with that, we are coming to a close of the inaugural session. On behalf of the organizing committee, I thank Director IITM Pune and Ministry of Earth Sciences, Government of India for the constant guidance, support and funding for the workshop. I also thank Dr. Karthik Balasubramaniam from Agarkar Research Institute, Dr. G.R. Tripathi, Dr. Devapriya Chattopadhyay and Dr. Shreyash Mandave from IISER Pune and Dr. Rajni Panchan from Savitribai Phule Pune University for providing lab facilities for the training workshop. I thank AOQR working group members, particularly Dr. Vinita Partyal, for helping in finalizing the format and structure of the workshop and constant guidance too. I thank all the resource persons for taking out time of your schedule for this workshop. I thank the IITM administration, accounts, general administration, and computer division for their support. The division of desk has been a key player in handling the back end of all the logistics. So I thank all the desk members too. And I thank all the participants, last but not the least, definitely, for turning up for the workshop. Thank you, everyone. Now, before we close, there is just a set of instructions which I would like to tell you all. So please do follow all of them. First is right after this, we break for a high tea, and then after the high tea, we go for a group photograph in front of the library building, which is the building behind this main building. After the group photograph, the entire event will take place in Aryabhata Hall, which is in the second floor of the library building. So the same place where you go for a photo, you just climb two flight of stairs, and you will reach the Aryabhata Hall. Please do wear your ID card at all the times because it will help us identify that you are a participant of the workshop. Please be sharp on time, as Dr. Naveen Gandhi and Dr. Vinita have already told you, because it will help us to organize everything better and for all of you to learn everything better. All the participants would have received meal coupons in your registration kit. Please carry those coupons for respective meals. You will receive a certificate for this training workshop. However, it is mandatory to have attended at least 80% of the lectures in order to receive that. So please make sure you attend the lectures and also you sign on the attendance sheet. For any other queries, please do not hesitate to contact us. And this is one of the first of its kind workshop where we have like lab training in every second half, and you will be traveling to different places. I request you all to be very cooperative and very responsible for this. Thank you all. Yeah, let's go for the height across the board.
So good morning all. So we are a little bit actually advanced in our schedule. We are supposed to start at 11, but it's good actually we have started early. There are some technical things because we are going YouTube live also, and the people from BIMSTEC countries have also joined on this YouTube live. So and some because I in the morning session I told you that almost 300 applications came, and we could only selected 50. So maybe those students can also learn through the YouTube live. So I welcome Dr. Sushma Prasad. So to start with this lecture series. Thank you.
Thank you, Naveen. Today my presentation will focus on archives and proxies and the potential and limitations of these archives and proxies. Here, right at the beginning, I would like to emphasize what I'm presenting is teamwork. It's not just me, but a whole group of students, Anup, Arshid Jahangir, Philip Menzel, Praveen Mishra, Priya from IITM, Niels Riedel, Shashwati Sarkar, and in the lower line, in italics, are us principal investigators. The students and postdocs do all the work and we do the talking. I think it's a good bargain. Next, first of all, why study paleoclimate? I mean, for me, the first thing is it's fun, but there has to be some justifiable reason for getting paid for having fun. So here are the reasons. You live in a monsoon country, in monsoonal climate. And when we talk about monsoon, it means different things to different people. Those living in Thar Desert, those living in Maharashtra, those living in Kashmir, for them, monsoon means different things. For some, it means rain, some means flood, for some, it means a drought. So there is a lot of regional differences in climate. That's one point, that we need to understand the regional climate in the past. Second is frequency of extreme climate events. We're talking about heat waves, we're talking about floods. Our worry is how are we going to survive in a global warming scenario? To predict the future, you need to understand the past. Second is ecosystem response. Yeah, climate is changing, big deal. Okay, you build reservoirs, you build dams, everything. But how is it going to impact the ecosystem? You've got biodiversity hotspots, you've got forests, we have to worry about agriculture, we have to worry about the ecosystem in the lakes. You need to understand the impact of climate change on the ecosystem. Finally, testing of climate models. It's a pity Krishnan is not here because I love to tell him where he's making a mistake. But I think paleoclimate data is very important for testing the past climate models to be able to interpret the future. Now, starting with paleoclimate, simplest is going to a library, doing historical research. Yeah, few hundred years. You can go to dendroclimatology, the tree rings. Hemant will be giving a more detailed talk over there. It's a really high resolution record. You can count ring by ring. You can go for seasons. But the limitation is you don't get tree rings which can go back to 15, 20,000 years. And also the distribution of such old trees is limited. You can.
Slides are not changing in the screens.
I did something wrong. To select a window, I think, right? Go there, please.
No, I have to select the entire.
Yeah. Not that. Oh, IITM, yeah, that's a talk.
Slide is not coming.
No, it won't. You have to select a window before it does that. Yeah. Now it will allow.
No, but when we go to the full screen, no, it will not allow.
Oh. Well, some technical hitch. Sorry about that.
So this is what teams now. We will do one thing, ma'am. So you just move it down by this way.
I can't show everything there. That's a problem.
So the browser is not supporting.
Or can you direct the camera over there? They don't have to see.
हाँ डबल लॉक एकच आहे एकच आहे शेयर नहीं हो रही क्योंकि वो ब्राउजर अलाउ नहीं कर रहा
Just move the camera there.
No, not camera.
I think YouTube streaming can be like this.
हाँ pen drive है
You want to do it? You can do it. Use best you want. Don't. I don't have a use best if you have it.
नहीं इनके पास होगी इनके पास है ना
आपके में से हो जाएगी.
Thank you, sir.
आप प्लीज
हाँ it works fine. It's fine.
We explained during my series.
तो शेयर करेंगे तो वो वो जो फुल स्क्रीन करते हैं ना
अगर स्क्रीन पर तो नहीं होता है हाँ या फिर इसको ही चेंज कर
मैम ये क्या दिख रहा है task list cycle task list what all you want to do this one display settings bell shape duplicate okay
Can you change the slides? Use the change the slides and see if it is working.
okay
It's great.
Well, I hope you're all awake.
Yes.
We got the technical hitch solved. Thank you. All right. So paleoclimate. How do we study paleoclimate? Again, you look at the historical records. Goes back a few hundred years. Or you can look at the tree rings. That Hemant Burkafter is an expert on this. But tree rings, you cannot get a continuous record of several thousand years. Plus, the distribution of old trees is limited. You can work with corals. They're really beautiful, but it's very great job. You can work with boreholes. I think there'll be talk in the workshop, somebody else discussing that. You can work with ice cores. I will not recommend it. I don't like the cold. Or you can work with sediments. This is the best because I work there. Or you can work with stalagmite. They're also okay because Naveen is working there. Now, each of these archives has its limitation. You can see is this how far it can go. Yeah, only up to a few centuries, or you can go up to thousands of years or millions of years. But what you gain in temporal extent, you lose in resolution. You cannot go for high resolution year to year or sub-decadal changes. So you have to find a compromise depending on what you're looking for.
Can it be full screen? Because I don't think so back to
This is full screen.
full screen नहीं होता.
Well, from my side, it is. You go there, go there, go there. Oops, still.
Right वाला panel बता दो.
Or
वो क्या लिखना है उनसे पूछो.
Try that. Second.
okay, to end this and then we try again. And then go again and try, please. Yeah, so far.
Now on Teams we get the other.
Okay.
But
I hope it stays like that.
Sorry.
All right. This also we discussed. You may get a very long record from ocean sediments, but then you lose out in time resolution. How do you select an archive? I use what is called as a lab test. Location in a climatically sensitive area, and you have to find a sensitive archive. If you're looking for high resolution continuous records, it's useless going to floodplains, for example. Okay, and proxies. You have to have a proxy that is sensitive to climate change. Second is temporal extent. I like long records, high resolution, and chronology. This is something Krishnan mentioned, and all of us have faced a problem not finding good dates. We'll come to it. Selecting lakes. What do we look for? When I say we, I'm working with both Anup and Praveen, and we like to go for closed systems. It makes no sense if half your record is missing because of some flood, or somebody has chopped out part of your tree, or stalagmite is broken. Varved sediments, annual resolution, season to season. I will be coming to that. They are ideal. Then you should have high sedimentation rate, plenty of biological material, because like I said, it's not just enough to look at paleoclimate change. You need to understand how it's impacting the ecosystem. And long record in lakes or outcrops. And if you don't get this, you work with whatever the hell you find. You have to find a compromise. Now, what is a proxy? It's an indirect indicator of past climate. Okay. We use seasonally laminated valves, oxygen isotopes. Naveen will be talking about that as well. We use pollen. We use bulk organic matter, and there are lots of others that Praveen Mishra will be discussing later. So I'm going to discuss some of these proxies in detail and tell you what are the plus and minus of this. This is the first project I worked on when I moved to Germany, looking at the 8.2K event using biogenic valves. Now, what are biogenic valves? These are seasonally laminated. Hey, Mant, they're better than your tree rings. In winter, you have the deposition of clay. In spring, you have a specific type of diatom, stephanodiscus, that grows over there. Then in summer, you have Asterunella formosa. Then in summer, you've got calcite formation. Then in fall, you've got diatoms. And all these you have within 1 year. It's a beautiful archive.
How much thickness?
Sorry?
Thickness of each valve?
Sub-millimeter to millimeters. But diatoms are not an easy proxy. It's not one-to-one correspondence. It's a very complicated one. And the disadvantage, you have to sit for hours at the microscope. It doesn't look like very high-tech that you run in a machine and print a publication. It's a lot of hard work. And how do we work? Okay, when you start taking cores from lakes, you don't take a single core. We take multiple cores, and you have to be able to correlate them. Okay? And what we did in case of Holzmar was to look at the marker laminas, micro marker laminas we call them. They were correlated throughout the cores. And over 1,000 micro marker lamina were identified by a student per tribe. It was almost 3 years of work, which means all 3 cores were correlated on millimeter to centimeter resolution. You can't go better than that. And then came Sushma. This is what I was working on. It's working here, but yeah, sort of. So I'm not correlating according to depth. I'm correlating according to micro marker lamina because the depth may be different, resulting from differing sedimentation rate. And here is the age. This is modern, and this is 12,000 years. And we have a floating valve chronology that was anchored to radiocarbon dates. This is the 8.2K event here. Pay very careful attention to this part. This is missing. Okay, I'll come to it. So this is Holzmar data in the upper part. Yeah. All right, let me see if this works. In the upper part are the valves. In the lower part are the. How does this work? Do I need to hold it down or? Now it's working or no? Yeah. This is the Holzmar valves and this is the grip data because we all like to compare our records with others. Okay. So we look for similarities. We found some events. Did the correlation. Don't do it this way. I was young and I was stupid. Okay. This is a shortcut method. Later, we teamed up with mathematicians and we did a more detailed correlation and it confirmed it, but this is a risky venture. And then we started going into, I started going into details. This is winter. I looked for over 200 years. How did the winter lamina change? What is interesting is that calcite has disappeared over here for almost 190 years. Calcite dissolves when the waters are cold, when the climate is cold. And then you notice that the winters were drier. What is important information from this seasonally laminated valve is not just you can get different types of seasonal signals, but also the duration of signals. You can see this is dry over here, this is dry over here. There are several events.
Does only calcite or even aragonite?
Aragonite also. Highlights. I mean, we were very happy. We published it. Done. It wasn't done. I'm criticizing these projects because I've participated in them and I know the story behind it. And I think it's not fair to criticize other people's work when they're not present, but I can criticize my work. So behind the details. Now let's go to this part. Notice carefully on the left side, there are lots of cores. This D, 3G, we had multiple cores. And all of them, when you look at the floating chronology, it matches beautifully. When you go to the top, and then I started looking at it. I started looking at the lamination quality. This 1 is the best and 4 is the worst. And you look over here, as you go near the top of the core, the lamination quality changes. It's not good. So when what I call a WAV and what you call a WAV becomes different. Okay, the seasonal information changes, your chronology changes.
Such a question. Here's the top one missing. How do you bracket those WAV data?
But
How do you bracket those WAV data?
I'm coming to it. So how do we bracket the WAVs? It's a good question. Like I said, Bert Wright, he did the best possible work. Okay, correlation. Then I started counting, like you said, bracketing the counts. On the left side, you're seeing the difference in WAV counts. What Ryan counted versus what Prasad Sushma counted. What Ryan counted versus Sushma counting. Ryan versus Zolitska counting. Ryan versus Bayer counting. And as you can see, in the upper part, there's difference of few hundred years. We don't like to talk about it, but this is reality. And we should accept that. There's no such thing as a perfect archive. The record should be reproducible. It doesn't matter who counts, we should get the same amount. If we're not getting it, you don't throw out the entire record, but you look at the uncertainties and you make provisions for it. Deal with it. The other project I worked on was in Lisan and Dead Sea area. This Dead Sea, and here is the Sea of Galilee. What most people do not realize is that both these so-called lakes were connected in the past until 15,000 years ago, when because of climate change, they split into two. So Claudia Begowski was the first PhD student I was assisting. And here also we came across seasonally laminated WAVs. In winter and spring, that's a westerlies area, you get the plastics. Ouch, sorry. Then in summer, wet summers, you have influx of this bicarbonates during winter and spring, and because of evaporation, you get formation of aragonite. When there's a dry summer, you get gypsum. And during massive droughts, you come across this gypsum and halite. All the signal is there in 1 year. This is Claudia's work, part of a PhD thesis. Look at the top panel. She reconstructed the complete lake level over past 11,000 years using a mixture of shorelines, WAV data. It's possible to get high resolution lake level fluctuations using these archives. I was working on this Lisan, this entire thing. The lake has disappeared, but the outcrops are still present. You can see them on the right side. These are some of the photos. What we did was to prepare polished sections, do a very high resolution correlation, and then start going into thin sections. So remember this diagram, what I said about gypsum indicating a dry summer. So when I started looking at the thin sections, you will notice these, there is secondary gypsum. Okay, over here you can see the secondary gypsum. This will give you a false sense of security. You will think it's a dry gradient. It is not. It's a post-depositional feature. If you're just using an equipment like scanning XRF or something, you get a signal, you think, rapid climate change. Rubbish. No matter how much high resolution equipment and great labs you have, the basic work in microscope is still very, very important. Now again, how do you count the waves? Here, as you can see, do you call it a wave or don't you call it a wave? Or is it just a small event? So here, again, I looked at thin sections from multiple outcrops, compared it and included an uncertainty. You have to have uncertainty. You cannot have complete perfect records. Let's be real. Waves are good, but they need to be interpreted with care. Now, delta 18O as a climate proxy. This work was done by Anup and Praveen. So delta 18O is normally considered to be an indicator of amount effect, like more rainfall, more negative thing, or precipitation to evaporation balance in lake sediments. So I'm going to show a record from Lonar Lake and Somuriri. But one thing most of us don't talk about, that there is no change in the moisture source or pathways. If your moisture is coming from Arabian Sea, it will have a different isotopic signal compared to the Bay of Bengal. And we need to be open to that. Look at the data. Delta 13C versus 18O, plots for both Somuriri and Lonar. We generally assume that if the correlation is high, then the system is closed. Yeah, but if you look at the Lonar signal, delta 13C shows a lot of variability. That is because of productivity impact. The phytoplanktons growing in the lake have taken up a lot of carbon and changed the signal. In Somuriri Lake, it seems as though there are two signals. There are. So we started looking at Lonar and Somuriri. If you look at this, I mean, blindly, without considering source amount changes, this is negative, so this side should be wet, right? In both the lakes. If I accept that, that means Lonar Lake was dry during early Holocene and Somuriri was wet, and opposite signal in late Holocene. Rubbish. Okay, don't trust a single proxy blindly. So,
like is also a proxy for temperature also.
When
you are like putting it to amount of it, have you taken care of the temperature?
In tropics, we don't expect much changes in temperature. I'm coming to this. So here, unfortunately, I had a very bright PhD student, Anup Ambili. So we also look at the surface sediments, the complete, signal. And he comes to me and says, but madam, there's a 4 per mil signature just in the modern signal from where the inflow is coming in.
That's in delta
18O. 18O, 4 per mil signal. Okay. I must say I was not very happy with Anup that day.
How far it is?
How far was it? 50 meters? 100 meters?
Yeah.
Yeah, about that.
What?
Yep, because it's fresh water coming in and you've got evaporation in the center of the day. Most of us do not pay attention to that. We just raise a core and bang, you're doing paleoclimate. But you need to understand the modern system before doing this.
Is it a stratified lake?
Sorry?
Is it a stratified lake?
Yeah, it is stratified, anoxic lake. Yeah, but still I have 20 per mil signal and I told Anup, okay, I take away 4 per mil, I still have more signal. And then he comes and says, no, madam, we still have the opposite signal. All right. Here, the source of pathways change. I'm not showing the biomarker data here because the talk will become too big. But what I'm trying to say is the risk of using a single proxy. Don't do it. And how do we know that this is not totally reliable? I will come to the data later, the rest of the data. Then Somuriri Lake. Like I said, it appears there are 2 signals. Well, there are. This was part of Praveen's PhD thesis. He showed that there is change in westerlies versus monsoon precipitation in this area that has caused this change. This was almost 24,000 years of record using carbonate data. So 18O is a good proxy, but it should be corroborated by others. Next, pollen. Well, I love and I hate this proxy. What we did, again, as always, we do a complete catchment sampling, everything possible. We go drill holes all over the lake, and then we start comparing the data. What we found from pollen is that when you look around the lake in the soil, there is very good representation of modern signal. But when you start going within the lake, you get different signal. Because you have contribution from wind pollen, you've got a contribution from water transport, size of pollen. So if you're using only pollen, your reconstruction will depend on where you have done your course. From the shore, you get one data, and from middle, I get another data, and we fight about it. That's not the way to work. Then bulk organic matter. By the way, this is a lake. Don't have any doubts about that. There are fish swimming over there. These are the phytoplanktons growing in the lake. And this is the terrestrial vegetation. Because bulk organic matter is also an indicator of what's happening in the catchment. So carbon to nitrogen ratio here is low and here is high. And trees, see two different types of plants. Drier trees have different type of signal compared to the wetter ones. But within the lake, the picture is
minus 27.
Roughly I've put it, minus 27. I'm sorry, I'm not able to hear.
He's saying minus many.
I forgot to write minus. I'm sorry. Typing mistake. Yeah. But if you start going into the lake, it's far more complicated picture because the plants are taking a lot of carbon from the lake water. How saline is the lake water? What is the pH of the lake water? And how much is the productivity? Because the more organic matter grows, more of the lighter isotopes it takes in. And when there is no lighter isotope left, it starts taking in the heavier isotope. All this you have to bear in mind when you start using organic matter. Again,
Delta 15 and you're attributing to? Delta 15 and you're attributing to?
That is again, atmospheric signal is 0, and terrestrial is about 7. For the lake, it depends negative or positive, depending on
productivity also.
Yeah, it depends. Of course, it depends on productivity. Both 13C and 15N co-vary when the productivity is higher. Yeah. But when you look at this, here also you have to be careful. Isotopic composition of surface waters can change because of evaporation that we found in Lonar, changing source waters that we found in Somorari Lake. That was really, really weird. We found that the source water is changing. But unless you do a complete catchment sampling, it's useless. And C by N. In Lonar, Anup came across some plants with carbon to nitrogen ratio of about 100. So if you are using only C by N as indicator, productivity indicator, you are in trouble because one sample from the catchment can completely impact your signal. And organic matter degradation, you have to check for that. Now working on lake sediments, how do we do it? When we go there, we go as rather big groups. We start mapping the catchment, looking for paleo shorelines. We map this, by the way, photograph is from Praveen's thesis. We look at the lake bathymetry, coring. Question is, do you take short cores or do you take grab samples? Depends on the sedimentation rate. If you're taking grab samples, it is best if you have high sedimentation rate. If it's a low sedimentation rate, then somewhere you're getting 5 years, somewhere you're getting 50 years. And modern bathymetry, hydrochemistry. Look at the water. You look at the rainwater. You look at the groundwater. What is coming in? You look at the lake stratification, complete mapping. You look at the seasonal changes. Field work. We collect all the sediments. We look at the geochemistry. We look at sedimentology, mineralogy, pollen, microprocess, everything. Hydrochemistry, we do seasonal monitoring. That's why our publications are slow, but it will be very exhaustive. And we look at the vegetation, catchment, soil, carbon isotopes, everything. And sediment traps, I will come to it. Because, if you want to understand how the climate is impacting the lake ecosystem, it is best to put sediment traps, collect monthly, seasonal as you can, and then try to link it with the meteorological changes. This is coring. Ravi, you were asking about coring. This first team is in Kashmir. This is Arshid Jahangir from Kashmir University and Praveen. This is Manas Balpuri. And that is in Somorari. These are the cores that we got. I'm coming to more details. Okay. What do we do once we have the cores? We take it to the lab. do the cutting, you have to have a really well-equipped, clean lab. Next, we have to do the correlation. And look at this. Here, it's different in the upper part, the cores. It could be because you didn't get the core top, or maybe there really is a change. You have to do cesium dating, lead-210 dating to figure that out.
Did you take any short core and try to see? They're also top or not there?
They were there. This is actually reflecting changes in the sedimentation process. That is why I say you can't just take one core and say done. Then we do XRF scanning. This is a photograph from Maru. After that, picking out material for radiocarbon dating, Anu found an intact leaf from early Holocene from the Lonar Lake. He did that. And we had a party that day.
Okay.
After that, you start subsampling the cores. Core storage, these are the unopened cores. After they are cut, you have to put them in D-tubes and store them in special cool rooms. Otherwise, you have fungus growing into it. I had that. Or you have secondary precipitation from interstitial waters. And you end up with rubbish signal. You do today and you do 6 months later, you have 2 different signals. So what do we do?
Just what temperature do you store?
4 degrees.
We do biology also.
That's really important. Otherwise, 1 year to next year, you're getting different paleoclimate. Okay. Now, coordinator. For all these projects, we have a coordinator. His or her job is to build the core composite, document the lithology. We want a standard procedure. It's not that Anup is doing one thing, Praveen is doing one thing, I'm doing one thing. There's only one boss there coordinating it. Sampling strategy is decided. Lake monitoring, chronology, data compilation. This is all done by discussion, but the information is distributed by one coordinator. Samples go to different teams. They do their work, but as far as possible, we try to use identical samples for all the analysis. So when I say leads and lags, it is leads and lags. It's not our imagination. All the data goes back to the coordinator, whose job is to compile the data and circulate it to everyone. After that, we have arguments because all of us think our baby is the best. So, well, we do have discussions, but we have an ironclad rule. You do not publish your result without discussing with others because I don't want 5 different stories coming out from the same core. After that, we publish the data. The job of the coordinator is not easy and you need someone big and strong and dangerous. I do the job. And now I will present what work we are doing. Again, I'm putting everything in alphabetical order. Cluster University Jammu, Praveen is working with us. French Institute Pondicherry. This is specifically your leagues. ISR Mohali, Praveen. Kashmir University, Dr. Ashit Jahangir. In Germany, Hamburg University, Potsdam University, and Senckenberg Research Institute. We have been working together since 2010 or even before that for a very long time, and there is a lot of trust and goodwill. So it works. What do we want to do? We want to look at the climate extremes all over India. We want to look at the regional pattern. We want to see what is causing it, and we want to see the regime shift. That's our objective. So this diagram was given to me by Priya she's here somewhere, I think. Okay, from IITM. This is what we call as classical monsoon. In June to September, you have green, lot of rainfall. In winter, it's dry. But we know this is not reality. You can have, this is the cold monsoon region published by Gadgil when you talk about all India monsoon. And then you have the teleconnections. You have, when you have monsoon break, you have El Nino, when you have Indian Ocean dipole, you will notice that the correlation of the all India monsoon rainfall is highest only with the core region, not with the other parts of India. It makes sense. Our climate is very diverse. So when you want to do paleoclimate research, first question is, what are you looking for? So here for selection of archives, first of all, I want a long record because early Holocene was warm. And now we again have a warming climate. So I want to see what is the frequency of extreme climate events in early Holocene, and then look at the modern day patterns, hopefully work with the modelers and see if we can find any sense. Geographical distribution, it has to be all over India. Ecosystem response, and find a good chronology. So first objective was to look at the cold monsoon, central India. We were lucky, we got into Lonar Lake. Maximum depth is about 6 meters, brackish, alkaline, and it's dominated by summer rainfall, and it's a closed basin. Again, like I said, we make holes all over the place. Complete documentation from Bombay to Lonar, an entire area we collected vegetation samples, we did soil sampling. So when we talk about some parameters, we are sure about that.
These are photo sampling or core sampling? Surface sampling.
Yeah.
These are grants.
I'm coming to it. This was done in cooperation with Professor Basavaiya from IIT. Without him, it would not have been possible, and very thankful for that. For this, Basavaiya purchased a platform, but I brought along a coring team from Austria and from Germany to do the work.
So this was a coastal core around. It was a coastal core around the lake.
No, it was from the center of the
Center.
Center of the lake.
You have to set up a platform.
Yes, yes. So,
Yeah.
let's see the picture.
Now, this is the core composite. And again, I will give credit to Anup. We found 3 zones, these bright yellow zones, which showed the presence of Galusite meter. It's a formed in very saline environment, and it's the first such documented case from India, thanks to Anup. And in the lower part, he came across bars, monsoon rainfall, and then summer evaporation. It doesn't look very clear over here, but it is clear. We did everything over here except microfossils because they were not well preserved and they were not recognizable. We did everything possible on this lake. We looked at sedimentation rate, carbonate isotopes, organic matter, geochemistry, everything. I will not go into details. We can discuss that later if you like. But these brown zones indicate these brown zones indicate dry period, and the dark brown zones very prominent droughts. Now let's come to the pollen. The red part indicates drier climate according to the pollen, and the D1 and D2, this shows hydrological droughts. In the sense the water chemistry is changing at a different rate compared to the pollen. It makes a lot of sense. You're dealing with 2 different systems, right? Vegetation responds at a different rate, and here we have got hydrochemistry.
Unless you're seeing more scattered, like in drier period at 4,000 years.
Ravi, I'm really sorry.
Is that more in pollens? You're getting more scattered your 4,000 year dry period. But generally, you don't see such a scattered one in India.
But how many times have you compared 2 different?
No, I'm not asking. I'm asking that would there be any reason for that?
Yeah, for that I'll have to show you a different publication that came out this year. But yes, there is a reason for that, how we are identifying it. So this is exactly why today when Krishnan was saying that one says extreme event, other says at different times, you have to have different proxies before you mix. I won't say one proxy is better than the other. You have to look at the overall picture. So what caused this? I mean, when you want to publish, you have to have a sexy story, right? So that time, Krishna Kumar's publication had come out talking about shifts in the position of the Pacific warm pool. So I said, okay, let's check that out. So first drought, look at that. And we looked at the Indo-Pacific warm pool. This entire brown shaded area is the modern zone for the IPVP. And the red circles indicate warm, blue circles indicate cooler Pacific pool. Okay, you will notice that the red zone is fairly wide. When you go to the intervening period, the hot pool is sort of shrunk. You go to the next drought and you notice that the hot pool, the red spots, they have expanded. So obviously Central Indian droughts are linked to positions of the Indo-Pacific warm pool. So what was our summary? Yeah, you can find.
Why did you choose to compare it with the IPW?
Because that was a hypothesis going around that it's a dominant factor. But like I say over here, I put a question mark. Are the dry periods linked to shifts in the position of the warm pool? It is one of the factors. I'm sure there are others. And now we are testing it, but for that we needed more archives from North India. So we have a Manasbal archive also from Kashmir. I'm coming to that. Yeah. So our next objective was to look for Holocene westerly variations. So for that, we went to Lake Somoredi, which was a bad idea. This is a very beautiful lake. 4,600 meters, 105 meters water depth. In India, we do not have the expertise, at least for us academic people, for coring. So I brought in a team from Austria to do the coring, UVTech company. This was one of the most difficult expeditions I had. 6 languages. People are talking to each other. They think they're giving the information. I didn't understand. My passport is missing. Oh, but we told you where it is. 4 religions. One doesn't want beef. One doesn't want pork. One is a vegetarian. I said, everybody gets vegetarian. Some want alcohol. Okay, you drink in a different corner. 3 countries, Austria, Germany, India. 6 teams, 3 from India, 3 from Germany. About 20% of the team fell sick because of altitude sickness, and we had to send them back. We did the coring in 2011. This is the platform. And I must honestly say, I was there just for the photograph. The young people did all the work. And here, next to Ben Vuneman, you can see Dr. Dinanath from IIT. He is a very quiet, modest, but a very good scientist. Ah, there is Anup. He's looking much younger there. What happened, Anup?
So you went in there and then you pegged to the bottom.
Yeah. This is photograph with the core. You can see the 2-meter long core we had. Here also, we have done everything. Again, there are multiple teams. I'm presenting it, but it's not just my work. Only biomarkers are pending, and Anup is interested in doing that, so I'll send in the samples from Germany. Again, this is Praveen's PhD thesis work. Did a lot of work. I will not go into much detail, but he could go into highly detailed reconstruction of hydroclimatic changes for the past 23,000 years. What else he managed was, using the carbonates and regional correlation, he could figure out changes in moisture source and atmospheric circulation. We also had cores from 2 different water depths.
Moisture source, how did you delineate?
Moisture sources, isotope changes plus regional transects. We took from Mediterranean all the way to Himalayas. Well, I won't say we did it, Anu Praveen did that. All the way, we took a regional transect and then we figured out how it happened. We can show you the whole paper, no problem.
No, that's okay.
It's possible.
It's important to know.
Absolute. If you just look at one lake, you cannot tell. You have to go for a transect. Yeah. And here we had cores from 40 meters depth and 105 meters depth. So by putting these 2 together, Praveen reconstructed the entire lake level changes, and he could show that in the older part, most of the rise in lake level was because of meltwater, but in early Holocene, it was because of summer monsoon. And you could see how fast the lake level rises. Somoredi is a huge lake. And now, regional transect. Krishnan is worried about differences. Well, they exist. At least for these 2 lakes, I can guarantee I'm on solid ground. You can see that Central Indian Lonar Lake, that shows far more changes compared to the high altitude Somoredi Lake. It's real. Now, next we come to forcings and regime shifts. There's a lot of mathematical data involved, which I'm not an expert in, so I will deal just with the basic. A regime shift occurs when an internal feedback or external forces triggers a different system behavior. That's technical language. Think about Kashmir changing into Thar Desert. That's what that extreme case. And this can occur because of external forcing. You can have solar insolation or ENSO, for example, or intrinsic. Intrinsic means something like a runaway car. It's out of control. It's changing. We published this in 2020. There's not enough time, so I will not go into detail, but the point I wanted to make here is it is possible to do it. We figured out what were the forcings, what were the leads and lags in the system, all of it. The other thing we did in Lonar in Central India, we looked at the plant diversity. How did it change in response to climate? That paper is coming out this year. Now, ongoing projects, what I'm showing now is unpublished data. Again, Holocene westerlies. We went to Manasbar Lake because Somoredi, there are a lot of hard water problems. Chronology is a pain, serious pain. and I cannot 100% trust the data when it comes to high amplitude short-term climate change. So we thought, let's go to Manasbal. Ravi will recognize that. It's an OPL project. This is the lake. Here we are working very closely with Kashmir University, Dr. Arshid Jahangir. Arshid is here in the back. Here is Anup. And I think he took the photograph to show me how hard he has been working. This is a platform. Ravi, the expertise is there in India.
It is okay.
No,
It is there.
you did it, I remember. I mean, you had a major action.
Trade secret, Anup and Praveen. And this is how we got it. Here are these two. That's Ashit and Praveen with short cores. This, they have a short coral with 6 centimeter diameter, which is not ideal.
Okay.
You need a 9 millimeter diameter, but Anup is trying to purchase it. We hope it works out. But here we had a very interesting challenge. We were trying to deploy the sediment traps. We thought, okay, the team, Kashmir University is really good. They know their job. So we thought, okay, we get seasonal variation. So we deploy the sediment trap and we go away.
What is evaporating sediment trap?
Say that again.
Evaporating, what is that? I know sediment trap.
Mhm.
What is evaporating sediment trap?
I will tell you. I'm coming to it. So then Arshit comes back after a few days and the sediment trap has evaporated. It's gone. Okay. So Arshit, I mean, he's a very nice man. So he goes and asks the local people, oh, my sediment trap is missing. Where is it? So somebody brings him the sediment trap. So Arshit, very kind man, he gives them a little bit of money, puts back the trap. Next day, the trap is gone again. So, I mean, it's a nice source of income. So that's why I call it evaporating sediment. Okay, so we thought, okay, we have to find another way. We need to be creative. So here what we said, okay, we have really high resolution short cores. Why don't we use that? So 1963 to 2012, this is cesium dated. I'm coming to it. And then Priya from IITM, she mapped all these trajectories, 1500 meters and 5000 meters. We have the meteorological data. We said, okay, let's take it another way. We have the climate data. Let's see how it's impacting the lake and the sediments. And what she showed that during the summer, most of the extra moisture is coming from the Bay of Bengal. All right, this is a cesium dating. This work was published. And then we started.
In Manasbal. In Manasbal.
Yeah, this short core is published. Cesium dating, yeah. This was done in Keele University, Niels Anderson.
Could you get Chernobyl peak also?
Don't.
Yeah,
Chernobyl,
by
1992.
88 में आया 86
Chernobyl. You should get there. Good.
Yeah. We are doing lead 210 dating also of fresh cores. So we have all the variation. I won't go into details for now, but using this here, we had a challenge. You have got calcite and gypsum. Normally you would say, okay, evaporative sequence, but this is the freshwater lake. So where is the gypsum coming from? So that again, Praveen developed this mechanism to explain it. Formation of pyrite, anoxia, everything. I'm not going into details. The point I'm trying to make it is, first step is also to develop a proxy. What is a indicator of which type of climate? Anoxia, ventilation, everything. And here we could coordinate the sediment data with the meteorological data on sub-decadal scales. Drier climate or warmer climate, it was reflected in the lake sediments. We have a 20-meter long Holocene sequence and over 40 radiocarbon dates. I have money for more, we are working on it. What I want to show you is the deepest core at 20 meters depth. You can see this calcium to titanium ratio indicates drier climate, right? You can see just how much detail we can see, early Holocene. This is supposedly younger dryas, but in between there is a better influence. Then we are entering the Holocene wet phase. It is possible to do it. And you can see the straight lines from the sediments. The coring quality is very good. It's possible to do it. And in India, I'm a proud Indian. We should do it here.
Yeah, हम लोगों ने किया.
कश्मीर यहीं से
यही से किया.
कश्मीरियों के साथ
Ask these Praveen. He was there.
कश्मीरियों के साथ
It's possible to do it, but we also have good archives. It may not be wow, but it's still very good quality. We are working on it, and we are also going for very high resolution pollen biomarker everything to see what was going on. This is a clean, sanitized version of age model. Here, pay attention to the emergent macrophytes. The plants we took for dating, they don't have any reservoir effect. But let's go to the next slide. They don't have any hard water effect. This is emergent macrophyte. There's nothing. Now, the red circles, that is a bulk organic matter.
Okay.
It's going all over the place. If you're not careful about the chronology, you can find every possible event under the sun and you can create new events of your own. You can talk about tropics versus pools.
Bulk ages.
Bulk ages, exactly.
Bulk you will have carbonates also.
See, bulk organic matter.
Organic matter, not bulk ages.
Because you've got organic matter growing in waters.
Exactly.
And we don't know what is coming in from the streams and surface inflow. You need to understand the system. We have these dates from 2014. We did not publish it because we were not sure. Unless I'm sure about my data, we will not publish it. So we try to, this is still in progress. We are trying to understand why this is happening. So to figure that out, we are looking at pre and post monsoon water, radiocarbon dating of water. That is in cooperation with PRL. We're looking at particulate matter. We're collecting it pre-monsoon, post-monsoon, lake top, lake bottom, everything. Really, really exhaustive study. It is not just enough to have a good chronology. You should also understand why you're getting a bad chronology. Well, like I said, we're still working. I'm not going to interpret this, but we're finding several events. Now, Krishnan's favorite, mineralogy. Here, occurrence of gypsum, I'm not sure if it is because of pyrite or not. There, Anup is helping out with biomarker analysis. We have done isotopes, carbon of organic matter. We have done everything possible on this except biomarkers, which is still in progress. At the bottom, the data is still missing. We are working on it. Now, Krishnan's favorite and also Naveen's 4.2K event. There appears to be some signal. What does it represent? I'm not interpreting yet. But remember, this is westerlies dominated zone. Okay? So bear that in mind, regional differences in climate. And new partners here, we have Dr. Amset from PRL, and we're also cooperating with the IVIN project, Deshpande and his group. Also ongoing, this is Phuket Lake. Here we are working with French Institute in Pondicherry. This is also an anoxic lake. It's not yet done. Again, coring. Again, Anup and Praveen, they look a little bit different, but they were present, both of them, and they worked really hard.
You carried the same dismantled and again.
We asked them. They know the trade secrets, all of it. And they're in India. It's possible to do it.
I do it a different way, but I do it.
But short coral, you don't need to worry about mantling and dismantling. What they did was they took two boats.
That's what I do. That's what I do.
But you can get maximum how much? 2 meters? 3? Not more.
About 3.2 in an Indian estuary.
This is the data we got. Now here, okay, you can't read it, but that was not my objective. What I was trying to see is in the lower part, you've got a lot of detrital material and you've got transported old organic matter. You may have a piece of wood, I did find it, which is telling me 4,200 years. Initially, when you look at wood, you think, oh, that should be a good signal. It is not. So again, we did filtering, took care of everything. This is where we did the high resolution study. So past 1,300 years, we've got high resolution data. And okay, next. What we're doing on the left side, you can see I've done a regional comparison. The yellow part shows the dry events. You can see, and all these are very, very well dated multi-proxy records. You're seeing that the dry periods seem to be shifting. I don't know why, to be honest, we are working on it. This is still unpublished. So these are, for the younger people, these are all the archives you can work with. It's going to be 3 to 5 years commitment. So be careful what you choose. But in doing all that, don't forget to have fun. It's really enjoyable. For me, it's a passion. It's like being paid to have fun. And that's what it should be like. All the best. Thank you. We will speak. I have maybe I have a hearing problems today.
Okay. So what is the question?
Good afternoon, everyone. Good afternoon, everyone. My name is Praveen from Rajasthan. I will just want to ask that you said that lake sediment we have collected from quarry. In lake, how we choose the location in lake? It will be continental or it will be a deep lake?
We do a complete bathymetric mapping. And based on that, we collect the cores, but we don't only collect the core from a single area. We collect from different ones, and then we start doing the correlation. There are two advantages. I mean, coring is extremely expensive. The advantage of taking multiple cores is, first, you can understand the sedimentation process in the lake, and you can also ensure that your record is representative. But you have to do the detailed mapping before doing it.
Hello, my name is Aryabhata. I wanted to ask, what is a sediment trap?
Sediment trap is basically a lake in miniature. You have everything from around the lake coming into the lake, which is what we're collecting, right? But sediment trap is same thing. Whatever material is coming into the lake will be deposited in the sediment trap. So if I collect after 3 months, I know it's only 3 months of record. And 3 months of meteorological data I have, and I can see, okay, warm summers or wet summers, so this is what happened. That's what it means, a collecting basin.
Thank you.
Hello, ma'am. It's Piranjan. So my question is, as you have said that drought events are associated with IPWP, so can it be linked with positive El Nino events?
Yes, it can be. But again, we should not close our mind to other options. I've been talking with Krishna, and he said tropical mid-latitude disturbance could have also occurred. He's right. But we had no record from North India, Himalayan region, which is why we decided to go to Kashmir to do that job. So I'm hoping we can improve, refine our hypothesis.
So in lakes, I'm Aharna, and in lakes, do you have any thing like biodiversity?
No, in these courses we didn't. None of these.
But you, okay. So how do you like? So if the lake does have biodiversity, can you still take codes from it?
Then we have a problem, and then we can't go for high resolution.
Okay.
Yeah.
And the sediment traps, are they located near the place where source water?
Yeah, we try to put it where the core was raised.
Thank you.
Hi, ma'am. My name is Rohan from Pune University. I just want to inquire about the core cutting. What is the suitable interval of core cutting? I mean, I don't want to mean the
sampling, you mean?
Yeah, sampling.
That course, you slice. We try to go as we have gone from 1 centimeter, and sometimes if we have bark sediments, half a centimeter. Yeah. So we try to go as high resolution as we can. If we have the chronology beforehand, it's better. But normally what we do, we try to get an overview, get the chronology, and then we realize, okay, here there is some event or here there is some change. Then you have the course, right? So then you start going into higher resolution over there.
And then, ma'am, sedimentation rates of the lake are usually not known before taking the samples.
No, we don't. But then we go for lithological changes. We see where we see the maximum change. For example, in Luna, we could see warp sediments very sharply changing into non-warp sediments, or for the droughts. So there we went into higher resolution. And then after, it takes about 3 to 4 months to get the age model. So once I get the age model, then I call up the team members and say, okay, here and here we need to go into more detail by the time the preliminary data is available.
So we thank Dr. Sushma. And so the basic take-home message is like Krishna sir also told in the morning that we have to have as many as proxy to come to any conclusion. Just we cannot rely on one proxy and just get to somewhere, right? So because she has shown many results where two different proxies are showing some different thing in the similar time period. So your chronology is also important, as well as the you have to discuss with even the people who are actually very critical of your proxy. So then you will have more reliable thing coming out from your own proxy data. So maybe so I will call the thank you, ma'am. Yeah, so our next lecture. So next lecture is on stable isotopes. So Dr. Shreyas Mandave is in IISER Pune. We would be talking about the basics of stable isotopes, because in Dr. Sushma's lecture also you have seen the use of stable isotopes. So stable isotopes are used in almost all the proxies. So let us learn some basics about it. Thank you. That's not mine. Next. Yes.
From sediments. The rate of food
Okay, nice. Live stream. ठीक है ना प्रेजेंट यहाँ पर ठीक है उस जगह नहीं है ना उसमें चेयर हटा चेयर पे तो कर दो ताकि वो वहाँ पे रहे ना you can move.
ये तो क्या
ठीक है जितना भी आ रहा है देखो आ रहा है ना डेस्कटॉप तो नहीं आ
Should we start? In the previous lecture, you heard about how exciting the Aryabhata investigation would be and how various proxies can be used to understand past climate variability. So, out of many proxies which are used, today in this lecture I am going to talk about stable isotopes, their applications in paleoclimate. So, I'll talk first about some basics of stable isotopes, terminology, what is fractionation, why isotopes fractionate, and afterwards I'll talk about some of their applications in interpreting proxy records of some of the types. So, Why do we need proxy record? Because the instrumental climate record which we have. So this slide shows number of meteorological stations on y-axis, and x-axis we have time. So the first instrumental record is from Chennai, which starts from 1830. So good special rainfall data set is available for only last 60 years. Good special resolution as well as we have time resolution. And we have these proxies which can go back in time much more than whatever instrumental data set is there. And we can use them to understand what is natural climate variability. So we have proxies such as lake sediment, speleothems, tree rings, corals, ice cores, sediment cores, and we also hear historical records. So out of these various proxies, some of them such as, let's say, speleothem, tree ring, coral, and sediment core, ice cores, they record oxygen isotopic compositions of various materials in them can be used to understand past climate variability. So we look at that. A stable isotope. So there are some isotopes which are radioactive. For example, uranium, lead, the systematic, or medium strontium, thorium, lead, all these things are there. So they are radioactive, they are unstable. But there are some isotopes which are stable. For example, hydrogen, oxygen, carbon, carbon 12 and carbon 13. I'm not talking about carbon 14. Then some isotopes, sulfur, nitrogen, helium. So they are not only radioactive, they are not also radiogenic. So whatever the elements are there, or isotopes are there, they are formed in nucleosynthetic processes. They are not subsequently changing. So anything that changes their relative abundances can be used to understand some process. How we look at them. Now isotopes, I need not tell you what are isotopes. They have different number of neutrons and same number of protons. And because they have very little mass difference, because addition of extra neutrons, they can affect chemical reactions. For example, this is simple example of water, which is normal water on the left hand side, and the water which is deuterated water, which is on the right hand side. And you can check the melting point of both are different, also boiling point of them are different. So even though their electronic configuration is same, but their physical properties are affected by their masses. So these isotopes can have real effects on reactions. Now, why stable isotopes? They have low atomic mass. They have relatively large mass difference. For example, if you look at the mass difference of deuterium and hydrogen divided by deuterium, it is 0.49. But in case of strontium, it is merely 0.01. So lighter isotopes, their relative mass differences are more, so they can fractionate very easily and they can affect chemical reactions easily. So there are other reasons why we use stable isotopes. Why ratios? So when we talk about isotopes, we talk about ratios. Ratios because it is difficult to measure. It is really difficult to measure. Just close this pointer. If you want to measure abundances, the precision is much poor. For example, there are various ways you can measure abundances. Simply, they have precision of 3 to 5%. But this mass differences and the effect caused by this mass difference is much less than that. So therefore, we cannot use absolute ratios, absolute quantities, but isotopic ratios can be very precisely given. Therefore, we use ratios. For example, that's it. It is written here 18O by 16O. So ratio of abundances of 18O by 16O can be measured more precisely than the actual abundances of 18. Now, because of this small mass difference, they fractionate. So what is the definition of fractionation? Partitioning of isotopes of an element between two coexisting substances, resulting in different isotopic ratios into substances, which is called isotopic fractionation. Let's look at one simple example. So we have, say, water at 20 degrees Celsius, which is in equilibrium with vapor. So R here indicates ratio of abundances of heavy isotope divided by ratio of abundances of lighter isotope. So look at the value of R there, 18R 0.0019857. And here, the ratio of 18/16 abundances in liquid is 0.002000520. Even though the difference is small, that can be very accurately measured because we can measure ratios very accurately. Okay, so this is what we measured, and then one thing you must have realized here, these numbers, they are in decimal. Right? So is it easy to communicate that number? Right, you have to remember this number. So we need to come up with some way to communicate that number, and what we'll do, we'll discuss it later. So whenever there is a reaction or process which selects one of these stable isotopes over the other, then we say there is a fraction shift. For example, in previous case, the lighter isotopes are more abundant in vapor than the coexisting liquid. Therefore, there is a fractionation, and the vapor prefers lighter isotopes. So that is fractionation. The characteristic of isotopes during fractionation are they are low atomic masses. Strontium fractionation is much less because we have seen the relative mass difference is less. They have large mass difference. They are largely covalently bonded in the compound, which again prefers leads to higher isotopic fractionation. And these lighter isotopes can exist in multiple oxidation state, form a variety of compounds. Therefore, again, the fractionation is different, and we can measure them easily. Generalities are this: heavier isotopes prefer solid phase. So when there is 18O and 16O, relative preference for 18O is heavier phase, which is liquid as compared to the gas. Then heavier isotopes prefer highest oxidation state. In biological system, lighter isotopes prefer product, and organisms prefer lighter isotopes. Now, as we discussed, the ratios are in decimal point, right? Small numbers in decimal point are difficult to remember. So get rid of this problem. We invent a term called delta notation, okay, which is nothing but we are expressing given ratio with respect to some standard, and we are multiplying it by 1000. So it is in per mil. If you multiply by 100, it is percent. Now it is per mil. So then we have then this per mil scale. Let's say it is delta 18 scale. The number 0 indicates the sample has same isotopic ratio as standard. Value positive indicates it as higher 18/16 ratio. That means our sample is enriched in heavier relative to standard. So negative number indicates it is lighter. Okay. Now there are various standards. For oxygen, it is VSMO, which is ocean water, which is kept in IITM Vienna. Then for carbon, we have PD belemnite, which is a fossil belemnite from Canada. For sulfur, it is a phase called twilight, meteorite, which is used as a standard for sulfur, and for nitrogen, it is air. So these, when the isotopes partition between two coexisting phases, in order to describe how they are partitioned, we use a term called fractionation factor, which is alpha. So alpha tells us what is the ratio of two isotopes, heavier by lighter, in reactant divided by product, or any two existing phases. For example, if there is equilibrium between water and vapor, then we call alpha fractionation factor between. So this number indicates fractionation factor. The superscripted indicates what we are talking about. 18 means we are talking about water here, oxygen isotope here. This is O is oxygen, and two phases are water and vapor. So when we describe this alpha here, whatever it is in the first is in the numerator, which follows in the denominator. So 18/16 in water divided by 18/16 in the vapor here, which is the second term here. So this is what we call fractionation factor. And let us again, there are two phases here, vapor, which is equilibrium with water. So 18R is a ratio of 18/16, and alpha will be given here like this. Now there are two ways isotope can fractionate. One we call process called equilibrium, and other is kinetic. So equilibrium is quantum mechanical phenomena driven mainly by difference in the vibrational energies of molecules which are taking part in. So we'll look at this in the next slide. Kinetic fractionation is unidirectional. It is incomplete, and it is due to differences in the reaction rate of molecules or atoms containing different masses. So again, we look at one example of this. Now let us look at this simple example where water and carbon dioxide, they are in equilibrium. Okay, so this is C16O. So both the isotopes of water are 16O, and in case of water, it is 18O, and this is our equilibrium reaction. So if you write equilibrium and equilibrium constant, so these are the parameters here. Activity coefficients are get cancelled out. So what we can say is the K value here at 25 degrees Celsius is more than 1. What does that indicate? It indicates CO2 slightly prefers 18O and H2O prefers 16. Okay, so this is the fractionation factor. Now equilibrium fractionation factor is because of the molecules which are involved in bonding. That is controlled by E vibration, and E vibration is one of H mu, and mu, which is vibrational frequency, is given by this formula. K is a spin constant, 1 by 2 pi, and this is the vibrational frequency is inversely proportional to square root of mass. So higher the mass, lower the vibrational frequency. So why isotope fractionate? How mass comes into the picture here? Through this, because it can influence vibrational frequency. So the frequency of vibration depends on the mass of the atom. So energy of the molecule also depends on mass of the atom. Now this is one example. Look at the E vibration of different molecules here. It is HCl, H is hydrogen, and in this case it is deuterium. Look at the drop in E vibration energy from 17,000 to around 12,000 joules per mole. Same is true for hydrogen in fluorine and in this. So if you write this reaction, delta G of reaction is negative, therefore reaction goes in a forward direction. Products are before reactant. Therefore, H2, which is deuterium, which is more enriched in HF than the coexisting HC. So this is how E vibration controls the distribution of isotopes into two coexisting places. So there are fractionation during physical processes. Mass difference gives rise to fractionation during physical processes. For example, diffusion, evaporation, freezing. Fractionation is the result of difference in velocities of molecules. Okay, we look at one example here. Let's assume CO is diffusing in air. So when CO is diffusing in air, then air can fractionate. So lighter CO goes ahead than the heavier one. Same is true for CO2, same is true for water vapor which is diffused. So in all your experimental work, wherever there is a flow, you should think of whether there is a kinetic fractionation. That needs to be corrected. So here you can again see the differences in the velocity of lighter and heavier. They are inversely proportional to square root of masses. So this is inversely proportional to square root of inversely proportional to square root of mass, and it comes to the denominator here comes as a numerator. So if you solve this equation, then you have this number. So regardless of temperature, the velocity of 12C16O is 1.0117 times that heavier one, 13C16. So in this process, there is a fractionation. Okay, so this is an example of kinetic fractionation. So this is a unidirectional reaction, incomplete reaction. There is no equilibration between product and the reactant. So this alpha, which is fractionation factor, is again controlled by temperature. And there are various equations which tells us about how two isotopes, which are distributed in two coexisting phases, their fractionation depends on temperature. Okay, so these various equations are there. For example, in this case, you can see this is temperature axis, and this is some sort of alpha axis. You can see alpha. So this is epsilon, which is alpha minus 1 into 1000, but basically it represents all alpha values. So as temperature increases, the fractionation becomes less and less. So low temperature processes are very effective in fractionating two isotopes. Now, for example, if the system is magmatic at say 1200 degrees Celsius, you don't expect much fractionation. But it is low temperature process, 20 degrees, 10 degrees, then there is a good isotopic fractionation. So lower temperature processes lead to maximum isotopic fractionation. So we'll discuss about some isotopic effects which are used to interpret paleoclimate records. One is Rayleigh effect. So this is map of northern or USA or North America, and these contours indicate delta D values, that is hydrogen isotopic values of precipitation. Can you see here? As you go towards northern side, the values become more and more depleted. That means the rain in say Alaska is much more depleted in deuterium than the rain in Mexico. As you go towards north, the rain becomes more and more depleted. So schematically it is shown here. We have ocean here, and let's say this is very high latitude area, or it is also true for high altitude area. So when water evaporates, nitrogen isotopes preferentially go into vapor phase, and as the moisture transport from the equator towards pole world, what is happening is the temperature is decreasing. When temperature decreases, moisture holding capacity also decreases. If moisture holding capacity decreases, it leads to rainout. So less and less moisture goes to the pole than the equator. So during this process, heavier isotopes are preferentially removed along the way. And when the vapor reaches the poles, it is much lighter. So precipitation, which leads to, also is isotopically depleted. So as we go towards pole, the isotopic composition decreases. So the rainout during its transit, how much it rainouts will decide what is the isotopic composition of precipitation here. If the conditions are cooler, then there is a more rainout and there is a very lighter isotopes. For example, you will see when we interpret the ice core records. And there is a mathematical equation which can be used to understand how isotopic composition of rain would evolve. So F is a fraction of moisture which is removed. Alpha is fractionation factor. R0B is the isotopic composition of vapor at the initial. And as the vapor passes from here to here, how would its isotopic composition would evolve is given by this equation, which is the Rayleigh equation. Also, it is expressed in this graph. This is again Rayleigh distillation equation, which I just described. There is also temperature effect. That means what people observe is on this axis, mean annual temperature is plotted. On this axis, delta ITO is plotted. Okay. So as temperature increases, delta ITO decreases or increases. That means there is a positive correlation. The lower the temperature, delta ITO is lower. Therefore, the precipitation here at lower temperature is enriched relatively in lighter isotopes. Remember, negative value of on this delta scale indicates the sample is enriched in lighter isotopes with respect to standard. Okay. So this is equation which have been derived. T is a mean surface temperature, mean annual surface temperature. Now delta ITO varies with this temperature. So again, this latitude effect, which is again I just described, which is minus 0.6 degrees per mil per degree of latitude. That is a real effect. There's also elevation effect because, as we said, as we go up, moisture carrying capacity decreases, it rains out, and this is how typically it is observed: minus 0.2 per mil per 100 meters of rain in oxygen, and this is in hydrogen. There is also something known as amount effect, which is if you read any paper about describing how to interpret isotopic composition of say tree leaves or speleotherina, So, or like, for example, biomarkers. One of the important parameter which is used is amount effect, which describes the inverse relationship between composition of isotopic composition of rainfall and the precipitation amount. Higher is the precipitation amount, more is the depletion. So that is the rationale behind interpretation. But as Professor Prasad pointed out, that the quantum of difference in the isotopic composition of proxy is too high to explain it by this amount effect. Therefore, you have to invoke something else, and that is changing my source, which is because of maybe changing position or the source region of moisture is far more distal than the proximal. That also can explain it. So in the literature, it is the amount of it is explained by three parameters. One is if you take more rain out from the system, then it is more closer to its same composition. Remember, during rain out, heavier isotopes are moved. If you remove very little, it must be very heavy. It should be very heavy. But if you remove more, it should be relatively lighter. So that is one way you can explain more negative values because of more rain. Other explanation is when there is a light rain, typically the raindrops are smaller, and those smaller raindrops evaporate at the subcloud layer. When they evaporate, lighter isotopes are driven out, so whatever remaining is heavier, and that heavier indicates the smaller rain, heavier isotopes. Again, inverse relationship. Another is when the raindrops equilibrate with the subcloud vapor, which is typically enriched in heavier isotopes, then also you can have the negative relationship between rainfall amount and delta T. So this is the one which is more frequently used and assume it is there in the system. These are rainfall amount. There is also seasonal effect. So if you are interpreting isotopic rainfall in a peninsular area, then we cannot ignore this. The point is, what is plotted here is delta T of rain on this axis and mean monthly rainfall on this axis, and also here it is shown months and isotopic ratio. As you can clearly see that the rain associated with October, November, December, so I'm talking about this part now, they are depleted with respect to monsoonal precipitation. For example, this southwest monsoon precipitation, the values are here. So southwest monsoon is enriched, northeast monsoon is depleted. There are various reasons given there. So there is a seasonality in the rainfall. Higher enriched isotopes southwest, depleted isotope northeast. So suppose you have a proxy which is recording both, then your ultimate what is being recorded is controlled by ratio of both, not the amount of one. So this also should be considered. Then let's look at some of the applications of isotopes in interpreting these proxy records. Now, before you use proxy record or isotopic composition of proxy records to interpret past variation in any climatic parameter, say temperature or precipitation, you need to calibrate the proxy first. Okay. Once you calibrate, then you can reconstruct using that calibration information. Let us look at how we can achieve the proxy calibration in natural setting. Let's say, for example, in a natural setting, we have a tree ring record, and tree is growing for, let's say, 1950 to 2000. So at the same place, we have an instrumental record, which is recording, same means nearby place, which is recording precipitation variability during that time. So we have an isotope record, we have actual precipitation record in a natural setting, and we can calibrate one against the other. One example is shown here. This is the teak record, tree record, and so this axis shows actual instrumental rainfall record. This shows the delta 18 of a tree record. Okay, so they are contemporary. You can see there is a correlation between both. So now we know that the proxy, which is proxy archive, is tree ring, what we are measuring is absolute isotopic ratio. It does respond to the instrumental parameter. So this is calibration equation. And once we calibrate, we can have this nice equations. So this forms basis for interpreting fast rain or reconstructing fast rain. Unless we have a robust understanding of how a proxy responds to rainfall, we cannot use it. And of course, there are assumptions here that the relationship is stationary in past, which can be contested. There could be various other parameters also which can, but on a broad scale, on a broad level, this forms the basis for past interpretation. The other way to calibrate proxy is to actual experiment. For example, this graph shows on this axis there is a temperature, on this axis there is a fractionation between 4N, which is grown in a tank whose water isotopic composition we know very well, and temperature also we can control. So this equation is derived from experimental work. So that's how we know how proxy responds to temperature and delta T. Now with this proxy calibration and this looked at, and let's look at how we interpret some of the isotopic archives. So ice cores, you know ice cores. There are multiple ice cores from Antarctica and Greenland. All these things are there. And you must have seen this kind of graph multiple times. So here it is shown temperature. On this axis there is a CO2, and heat shows dust proportion. Okay, so you're looking at here 1,000 of years ago. This axis kilo year, and this axis is the temperature variability. So this part is a modern period. The lowest value which is represented here is the last glacial maximum. Okay. So how do we get this information? How do we get information about temperature? How do we get information about CO2 concentration? How do you know about dust? What we have is ice core. So let us look at one nice example. So you know font, which is freshly called snow. So it is porous, and atmosphere can easily go. Atmospheric air can easily get trapped inside this. This is fresh snow. Right? So once it is compacted, what happens to that air which is trapped here? It goes into bubble. So these bubbles are there in the ice core. Okay. So when you take an ice core which is kilometers long, deep, and if you take a layer out of that, the air trapped in that particular layer is the air of that time. Okay, so we have a material evidence of the past. Now what, let's say this is one layer you are looking at. In that layer there are gas bubbles which trap that environment, that atmosphere. We'll have some dust particles, and actually ice is also there. So three parameters we have. So if you can take this layer out, melt it in vacuum, so you know what is the composition of air that time. And you can calculate what is the CO2 concentration in that atmosphere. The water which is there can be used to talk about past temperature. And dust particle can tell us what was the dust concentration. So this is again one interesting cross section of that ice layer. And can you see these parts? These are actual air bubbles which are trapped inside the ice. Now we can have all this data. The temperature is from isotopic composition of water. CO2 concentration is from concentration of CO2 in that trapped bubble, and dust concentration is also there. So this slide shows like N2O concentration, methane concentration, CO concentration, and delta D. And this record will talk about benthic for a nuclear record. So the coherence of this you can also see. Can you see here CO2 and temperature which is constructed from delta T no record? They co-vary. They vary very well. So we can say that CO2 and temperature are correlated. CO2 is a cause of temperature variation. So what is a way of interpreting this record? as we said, as moisture transports from tropics to the pole, if the climate is cooler, there is a more rainout on the way. The moisture which reaches near the pole, it is much more depleted in heavy reservoirs. If the temperatures are warmer, then there is a less rainout during the transit, and the water vapor which reaches at the pole is typically heavier, so lighter. And this is also seen in the correlation between surface ice and the surface temperature. Isotopic composition of ice and surface temperature also proves this correlation. And you can clearly see this ice core record. This is from 1, 2, 3 are from Greenland, and the lower record is from Antarctica. And there is a very nice correlation between the two. Now let's look at another proxy, which is called tree rings. And I think we will have a separate talk about tree rings and lab visit also. So one of the beautiful things about tree rings is their annual resolve. Even though the time span covered by them is few thousand years, not as compared to what we get in ice cores or lake sediments, but being annually resolved, and it has a wide spatial coverage, that is very important proxy for past climate reconstruction. There are various factors which control the oxygen isotopic composition of tree rings. We look at two important. One is this amount effect, which we already discussed. Amount effect is inverse relationship between precipitation and delta 18 of water. So this is what is observed on the tropical locations. Inverse relationship. So whenever this depleted water, so this is the oxygen isotopic variation. This is monthly precipitation. Higher the precipitation, lower the its delta 18 value. So which is amount effect. So the year when the precipitation is higher, delta 18 is lower. So same water to some process goes to the leaf, and in the leaf during stomatal opening, H2O goes out, transpired, CO2 goes in, and during this transpiration, the lighter isotopes are preferentially, they go out of the system and heavier remain back. And this is very important reaction, which is CO2, H2O, sunlight, and photosynthetes are produced, and then water. So oxygen here is from water. That oxygen isotopic composition tells us about, again, if you assume amount effect is there, the information about precipitation amount is preserved there. So it is there, then it takes part in this photosynthesis, and this is oxygen. So this can be used to synthesize leaf-wax compounds, biomarkers, or cellulose, lignin, all the parameters which can be used. This is the starting material for that. So that can preserve the isotopic composition of precipitation, which in turn can tell us about precipitation amount. So that's how we use delta 18O of various proxy, various like biomarkers or drilling record. Again, proxy calibration is involved. So in the training, unless you calibrate the training record with the nearby instrumental record, and both should be of contemporary period, then only you can calculate to get an equation like this and reconstruct it. So this is the reconstructed rainfall for location Parambiculam in Kerala. So what shown here is the instrumental rainfall record for whole of South Peninsular India, and this is Parambicular record. So you can see how very well they match. Okay. But remember, even if they match overall, there are some periods where the match is not correct. So here there is one-to-one correlation, but here they behave in opposite way. So that also gives the information why during certain period of time there is a one-to-one correlation, and during why certain period of time there is anti-correlation. That also can be used. So we showed that there is a higher rainfall during Little Ice Age based on training record. So break monsoon is again one important contributor which governs the interannual variability. So this year is a normal year. What is plotted here is day On this axis, June, July, August, September. In a normal year, this is the kind of pattern you get rainfall. But during break monsoon year, there is sudden gap here. Okay, and remember, teak trees in this area, they are growing from June to October. So isn't it interesting to know whether this kind of gap, whether it is reflected in the tree paper or not? And indeed, we saw it. What we did is, each annual layer, we subdivided into multiple layers. So typically, this is growth accrued during June to October. If something happens like this, there is a high chance that some of the parts which are there inside will also show that effect. Okay, and this is what we showed. And this work was done in collaboration with IITM. The samples were collected by them. I think Burgankar sir is there. So he collected those samples. So you can see this, the year is 1971, and which is a very prominent year of break monsoon. So basically, by looking at this inter-annual isotopic variability, there is a way to reconstruct how frequent were past break monsoon were the past break monsoons. That also can be studied by using intra-annual tree isotopic variations. Now let's quickly look at what controls the isotopic composition of foraminifers. Okay, so data 18 of foraminifers, which reflects 18 by 16 in foraminifer. It is controlled by delta 18 of seawater and what temperature that is at. The forams which are plantic and the forams which are benthic, they respond to these two parameters in a different way. The benthic forams, they are minimally affected by temperature because at the deeper level, ocean temperature doesn't vary much. But in the shallower level, the ocean temperature can vary significantly. So plantic ones, they are more affected by temperature, but benthic ones, they are not affected by temperature. Okay, so but both are affected by this delta 18 of seawater, and which we call as a ice volume effect. What is ice volume effect? During glacial periods, there was a more snow, so more lighter isotopes are locked in the glaciers. The water which is remaining is relatively isotopically heavier because it is a simple mass balance equation. If you remove lighter, what is remaining behind is heavy. So this is glacial condition where a lot of lighter isotopes are trapped in ice sheets, and this becomes heavier. So because of ice sheet formation, significant ice sheet formation, the delta 18O of water becomes less. Sea level also drops. So this we call as ice volume. In ice-free conditions, because nothing is trapped here, so this is close to 0. Now this is the ice volume effect, and delta 18O of both plantic and benthic, they are affected by this ice volume. So this slide again summarizes what controls the isotopic composition of foraminifers. One is some local conditions. There is also salinity effect. There is also ice volume effect. And combination of this, or cumulative effect of this, controls the seawater data value, and which again affects the delta 18O shells. Now, you can reconstruct past temperature based on what is the isotopic composition of foram and what is the isotopic composition of seawater. Based on these two, you can calculate past temperature variability. And this graph shows delta 18O of foraminifers from deep sea pores. On this axis, now we are looking at a time scale 800 kiloyears. Okay, it's not short time scale. On this axis, there is a delta 18O with respect to a standard called VPDB. You can see here clearly, and these fluctuations are called as marine isotope stages. So how do we derive that? These are from deep sea foraminifers. drill ocean core, find out how it is varying. And they are numbered in a different way. So one which is shown here represents last glacial maximum. And these are warm periods, the top ones, which are indicated by odd numbers, and even numbers are indicated by cooler phases. So these marine isotope stages, they talk about long-term climate variability, or we can call it as a based on Milankovitch cycles, how these parameters vary. And it is very interesting to know that the top one is these marine isotope stages based on this independent proxy, based on delta 18O of foraminifers. The bottom 4 ones, they are ice cores. So one record we have benthic foraminifer, the foraminifer record, and we have ice core records. Look at both, how they vary. Now these are very finely resolved, we have good resolution, but these don't have very good resolution. Can you tell why? Can you discuss this when during previous presentation? Can you guess why this is more smooth? Why foraminifer records are more smooth than the ice core records? Yes, time scale is same. Why aggravation? Because they're mixing. The resolution goes. Okay. Now, interestingly, we can reconstruct past sea level using delta 18O foraminifer. So this axis is again time, and you are looking at the past sea level fluctuations during last glacial maxima. This was the topography. Okay. So how we can use? We know that delta 18O foraminifer is controlled by delta 18 of seawater and temperature. There are ways by measuring magnesium by calcium ratio and get rid of this temperature effect and only talk about delta 18 of seawater. So what it was found that glacial interglacial range in delta 18O is typically 1.3 per meter, and which corresponds to 140-meter drop in the sea level. So what we know is, let's say if you form 100 meters of, let's say you drop sea level by 100 meters, that moisture is now trapped in the polar caps. If you remove that, what should be the isotopic composition of remaining seawater? That seawater gets preserved in delta 18O forever. So based on that, you can calculate relative sea level. There are coral records as well, and this is how the coral is drilled, and this is distribution of corals in tropical land. These are some of the corals here shown, and what is being measured is delta 18O, delta 19C. So what is inferred is SST, rainfall, IDCZ position, SST. So this can be in front of the coral records. So what is rational variant interpretation? Growth band thickness is inversely proportional to temperature. SST, sea surface temperature. Density of coral band is proportional to SST, sea surface temperature. Oxygen isotopic fractionation. The delta 18O decreased by 0.22 per mil per degree change in SST. That is also used. And whenever there is a more rainfall in the nearby region, so there is a higher flux of water, and again through amount effect we know higher rainfall, lower delta 18O. So therefore that also is used. And based on this sea surface temperature variation, there are very nice past ENSO reconstructions because they have reconstructed sea surface temperature in the various parts of the ocean, and that is used to reconstruct past ENSO. I'll quickly describe the Sibyliotherm records. You know what is stalactites, stalagmite, and flowstones. Rainwater percolating in the soil has high CO2 partial pressure than the cave atmosphere. Why? Because roots are the one which respires maximum CO2. Also, there is a degradation of organic matter. The combined effect of that leads to soil CO2 concentration much higher than the air CO2 concentration. Remember, soil CO2 has very high concentration than the air or cave distance. So once that water, which is rich in CO2, and CO2 chemically dissolves in water, forms bicarbonate, carbonate, all those things, species, and it can effectively leach out calcium from this. And when it comes inside cave, where the ambient CO2 is less, but the soil CO2 is very high, the water which is entering the cave has very high CO2 concentration. That gradient in CO2 leads to CO2 degassing out. So once CO2 degas out from the system, the equilibrium is disturbed, which leads to calcium carbonate precipitation. So you can clearly see here. This is the equation: H2O from rain, CO2, air, then CaCO3 dissolves, it produces, and calcium carbonate, which precipitates inside. That oxygen is from water oxygen, which again, if you assume rain, the amount effect. So the isotopic composition of water in calcite represents the isotopic composition of this. Again, one example is shown here. This is Akalarbi cave from Karnataka, and on this axis there is a time, and on this axis there is a delta H now. On right hand side, we have talked about what is mentioned is rainfall amount. So how will you know rainfall amount? Again, assuming amount effect. So either you assume or actually measure there at the spot of sample collection. And then you can talk about this. Is the same. Let us look at the last couple of slides. The lake records already, Professor Sushma Prasad already mentioned that. These are fine grain sediments in the lake or deep ocean sediments. One of the processes which is used in the lake record is leaf wax compound. I think Anup is going to talk about this in more detail. So again, primary interpretation is these leaf wax compounds, they inherit the isotopic composition of precipitation. Whatever precipitation was there during that time, that leaf wax preserves that, and eventually that organic matter goes to the lake bottom and we can reconstruct past. So two compounds are most important. One are N-alkane and the others are alkalic acid. So these are straight chain carbon hydrogen compounds, and the length of this carbon chain would be, say, from 20 to 35 kind of thing. And at each corner there are hydrogen atoms, and isotopic composition of that hydrogen reflects isotopic composition of precipitation. Again, you can see there the amount of rainfall is controlling hydrogen isotopic ratios, which controls the isotopic composition of N-alkane and alkalic acid, the experiments. She has already mentioned, I think, about this record. This is lunar rate record, which is here, and you can see delta D variability. Now the question comes, this almost 40 per mil drop in delta D. Can we use amount effect and infer about rainfall variation? Part of that variability could be because of amount effect, but part of it because of the moisture source is not the same. Either moisture source is not the same, or the moisture is coming from more distal sources. There are some studies which suggest that, I think in your paper you mentioned that because northeast monsoon is more depleted than the southwest monsoon, if you change the relative proportion of northeast monsoon more, there could be this drop. But there are other studies which talks about hydrogen isotopic variation in the Godavari basin area. They say that the moisture is coming from more distal sources. For example, not from the if you look at the wind trajectory in Northern Indian Ocean and Southern Indian Ocean, moisture can come from both. But whenever there is a a large drop, which was explained by moisture coming from, okay, let's say more distal sources like this from southern Indian Ocean. So with this, I stop my presentation, and if any doubts, we can talk. You can talk.
Questions? Doubts or something?
Sir, if we talk about speleothem, which will be you prefer, like stalagmite or stalactite? In best sampling.
We have down to speleothem, stalactite, is nothing. Stalagmite, right? So
Stalagmites are those stalagmites grow from the bottom. Actually, their growth axis is so perfect, or you can say that when you have a proper lamina, and so the growth axis defines the your sample. So better to take a stalagmite.
Thanks.
Yeah.
So very basic. Like you said, from the ocean, when it's going towards the poles or the higher altitude regions, the isotope is depleted. Now, this is when we talk about the case of ocean to landward. If we talk from something like westerly contribution, then what is happening? If the westerlies are coming, they're already depleted. What would be deposited in the high Himalaya? I'm talking in context to the Himalaya or the snow that's getting precipitated there during the winter months. So that's a westerly source. How does isotope work there?
Yeah. So for westerlies, the moisture source is basically coming from Mediterranean, that region, right? So there also there could be ultimate moisture source is either ocean or recycled moisture. So if you consider the dominant source is an oceanic source, during path also there is a depletion. So as it goes, so the isotopic composition of snow, which is looking at the say Kashmir now, okay, which is affected by how much it has rained out before the moisture parcel reaches there. So same thing applies and that case also. So more depleted. So more continental transport, which is also known as a continental effect. As you go more away from the coastal area, the isotopic composition becomes different. So which is seen in, for example, rain in let's say West Bengal, rain in Kanpur, and the rain which reaches in Delhi. So there is this continental effect.
Good question. Michael Parul from Lucknow. My first question is how to compare paleoclimate of two different regions in a specific time window.
To compare paleoclimate of two
different regions in a specific time window.
How to? I didn't get two region. I know, but if you have a well resolved, you have good dates of both, then you can compare it.
So are you referring to the microclimate? Yeah, something like that. He's asking about microclimate.
Local climate. So it depends on your characterized process. Let's say there is three record and speleothem from two different regions, and you want to compare it. So first of all, the causal mechanism for two locations may not be the same. So a priori, expecting both should behave similarly is also not correct. Okay. So it depends on what is controlling. For example, the sediment record and ice core record, they both co-vary because both are responding to the Milankovitch cycles in Earth. So there is an inherent, I mean, we expect you can compare these two records. But for example, let's say you want to take a lake record, which is dominated by westerlies in Himalaya. and you compare a lake record from Kerala, which is dominated by monsoon. So the factors governing if they are both are different. So why do we expect them to correlate? Unless there is something which is controlling both. So a priori expecting a correlation is not a good idea. But now suppose they are both are affecting by same, then if you have tight chronological control, then you can compare. Did I answer your question?
And second one, which software is there to plot paleoclimate data with a high resolution?
It's software. Just for plotting.
Yes.
You can use right? How plotting software controls the resolution. You can use MATLAB or you can use
Sigma plot.
Sigma plot, you can use Excel also.
Thank you.
Thank you, sir, for this nice presentation. My question is related to the isotope ratio. Suppose we are going from suppose Pune and going toward Himalaya and Trans-Himalaya, and temperature decreases in general. So, is there any isotopic anomaly from here to the Trans-Himalayas, or it is applicable to universal applicable? Will there be any anomalies in isotope composition?
So you are talking about, suppose if a moisture parcel goes from Pune to that, what should be the effect?
Yes.
Generally, moisture parcel doesn't go from Pune to that Trans-Himalaya. It goes from the other way. But anyway, so as you remove moisture from this whole initial moisture, say bulk, then it becomes lighter and lighter. So either you can remove by rain on a plane, which is called continental effect, or you can also remove as the air parcel moves up and temperature really drops, moisture holding capacity decreases. So as go up, then there is a decrease in isotopic composition. So cooler one or more distance from the moisture source or more altitude, more latitude, the isotopic composition will become depleted.
Good afternoon, sir. This is Sanchit Tiwari. I'm from Pune University. So my question is, like many of our teachers, they are working with the stalagmites, right? So, sir, can we do the similar isotopic testing with the carbonates which are getting deposited near the root zones? As many of our teachers, they are working with tree rings and stalagmites. These are different proxies. So, can we use the carbonates which are getting deposited near the roots?
So, you are talking about pedogenic carbonate,
yes,
which are forming in this one.
Yes, around the root zones.
Yeah. So, again, what leads to the formation, precipitation of carbonate? One is there should be calcium, there should be enough CO2. So when CO2 degasses out, it can lead to precipitation, which is the case in case of stalagmites. It can also precipitate when you reduce water content, because the evaporation of water, it leads to supersaturation of CaCO3 and it is going to precipitate. There are both mechanisms. Now, temperature inside the cave, because it is protected from the atmosphere, it is in general, if the cave is not well ventilated, the temperature is same as mean annual temperature outside. The temperature fluctuation is less. But if you look at soil environment, there is no control on temperature fluctuation. Okay, here the layer by layers it is coming, precipitating. There are also layers, but the system is more complicated there. Evaporation, again the precipitation. So many things can happen in pedogenic carbonate. Interpretation of that is not very straightforward and easy as compared to this. So you have to think about variation in delta attenuation of rainfall, variation in temperature, precipitation, deprecipitation. So the system becomes a little bit complicated.
So, sir, the system is not closed, and the biodistribution thing that you mentioned, the resolution won't be that clear.
It is a bioturbation I won't use, but precipitation, deprecipitation can happen. So that can complicate the system. And therefore, it is much more easy to use these PLMs than the.
Can you briefly elaborate on the DX sensitive effect on the paleoclimate and meteorological patterns?
I don't have slide, but let's say D excess is deviation from expected delta 18 and delta D relationship. Is a d-axis. We don't have board. So that is d-axis, right? Now d-axis is controlled by source itself. For example, the ocean is the ultimate source. The relative humidity over the ocean controls the kinetic fractionation occurring during evaporation. That controls the d-axis. So the relative humidity is lower. There is a higher d-axis. Okay, so d-axis is controlled by source itself. There are various processes which is shown. Typically, it is believed during once the cloud is formed and there is a rainout. During that process, d-axis doesn't change. Okay, but there are some papers which contest this idea. In one of our papers, we have shown the d-axis of rainfall also vary when the raindrop leaves the cloud. At the base, when it evaporates, the lighters are gone more, so d-axis changes or equilibrates with the cloud-based vapor. So d-axis can vary because of this source. D-axis can vary because of precipitation post-condensation processes. Precipitating. It is evaporation and equilibration, and that is rain. So the d-axis, what you are observing now, are affected by source moisture, source region of moisture. Let's say some region of the ocean where humidity is higher, the d-axis is different. The d-axis of rain associated with westerly is higher. Why? Because your moisture source is from more dry regions. So that's what we can talk about d-axis in rainwater. So same is true about d-axis in, let's say, ocean core. It depends on humidity conditions over sea surface. Primary control.
You also explained the post-condensation process like kind of expression. So, is there any combining effect of vertical velocity point?
Now, again, it is controlled by drop size and how fast it is going. If it has to evaporate, if it is a smaller drop, then it has a larger surface area normalized by volume. Okay, so then evaporation effect is more. So if it is drizzle or light rain, it is more affected by d-axis. If it is a larger drop, which has even the higher surface area, but the volume is much higher. So relative surface area is less, which are affected by this. Now terminal velocity of larger is more, lighter is less. So if it is coming slowly to that a dry layer at the cloud base, which is subsaturated, then its d-axis will be more affected. So velocity comes through drop size distribution and their terminal velocity.
Good afternoon, sir. I am Diya from IITM Kolkata. Can I correlate the MI's ages with the terrestrial sediment ages in global changing?
What you are correlating? Which parameter? That's oxygen isotope. So oxygen isotope here in the marine stage are mainly affected by alpha. Okay. Now, and the terrestrial ones, let's say speleothem, you are comparing, right? They are affected by what? Again, isotopic composition of precipitation. Now, if the underlying phenomena which controls the delta 18 variability of precipitation and this, if they are the same, then both will be replicated. There are some cores which are some speleothem records from China which shows this correlation, and it is possible.
And sediment means the plastic sediments and correlate means.
I mean, when you are talking about
Means,
it's a clay content.
Huh.
Now, clay, see, the important point is every proxy, it's a clay content or oxygen isotope of speleothem or whatever other things are there. Their mechanism is different. Now, clay content should depend on if it is aeolian clay, what is the wind gradient, wind pressure gradient between the dust source and the sink region. Or if the tray is terrestrial, it will be controlled by the amount of weathering and how much rain carrying. So then it becomes a little bit difficult, like whether you can compare it. She wants to answer that.
Let me get the question very clear. You're asking if it's possible to correlate events on continent with the Delta 80 record, right? Yeah, answer is both yes and no. Yes, the events, the impact of this climate change is also preserved in your continent record. That you can correlate, but you may not necessarily get Delta 80 known as a proxy. You may get, like you said, amount of clay content, grain size, variability, something. So yes, it is possible to correlate. This has been done in case of Mediterranean area in late season. This Delta 80 node they correlated with shifts in lake level changes, which in turn is related to evaporite content. It is possible to do it. But regarding the Chinese caves and the correlation, there have been a lot of disputes about that, but it's just reflecting changes in source water composition. So I'm also a little skeptical. Yeah.
Thank you.
So we'll break for today, and so we'll all go for lunch. And for all the participants, lunch is arranged at the Victorian building, first floor. So probably you know, right? So these two will lead you to that place. And after lunch, you assemble near to the main gate, and we'll make two groups. One group will go towards the isotope lab, IRMS lab, and one group will go to the dendro lab. And after 4 o'clock, we'll have a small tea. Then we'll switch.